The broadcast is now starting. All attendees are in listen-only mode.
Welcome to the FenBC Fall Webinar Series. My name is Mike Cairns. I'm the Architectural Product Representative with Innotech Windows and Doors. I'm also a member of the FenBC Technical Education Committee. It looks like we have a pretty good attendee count here, so I'll get started. Our webinar today is High Performance Windows, a necessity for the BC STEP Code. Our speaker is Arman Mottaghi. Arman is the CEO of Lambda Science. Please note that the webinar is being recorded and the link will be sent out to all attendees. All attendees are muted and your webcam is disabled. During the webinar, Arman will stop at certain intervals and ask if there are questions. You can see in the GoToMeeting menu, there is an option for questions. Please use this area to ask questions. There's also a chat area, but please use that area to communicate amongst yourselves. Please join me in welcoming Arman Mottaghi.
Thank you so much, Mike. Thank you Zaina for having me here. I'm just going to share my screen real quickly. So I am wondering if you see my presentation now.
I do.
Okay, perfect. So it's a full screen presentation that you're seeing right now. And if that's the case, I'm good to go.
That is perfect. Thank you very much. I look forward to it.
Thank you. So hello, everyone. Great attendance, and I'm seeing the number is going up as well. My name is Arman. I'm the CEO of a local firm called Lambda Science. We help home builders, homeowners, architects, energy advisors, and all the stakeholders in the construction sector to build more energy efficient homes without an impact on their construction budget. You may have heard about our product, StepVin, which is available in many cities across British Columbia. And I will talk and show you the interface afterwards in case you haven't. I started this work about 3 years ago when I was a building energy consultant in projects of various sizes. And I saw the challenges that were being presented in high performance construction. The questions that were there were not really easy to answer. And we were really hoping that there was an easy way, which wasn't. So rolled up my sleeves and started working on this issue, and really excited to talk to you all about this experience so far and cover a few of these primer pieces. So in today's webinar, we are going to start with energy movement in the buildings. I think the audience is probably already very familiar with these backgrounds about the high performance construction and performance-based compliance, but I think I would like to give a certain perspective on those that hopefully starts to make a case for the changes that are necessary in the landscape of construction to really get to the STEP Code goals. After that, we are going to look at the blueprint of a high performance design and really complete that by having a case study. What is it going to look like in the near future, hopefully? The case for high performance windows have been created by the Vancouver Economic Commission a few years ago, actually not long ago, when they came out with the idea they had about how much each of the different components of buildings is going to improve or needs to improve in order to get there. So these markets that they were anticipating to see, without doubt for them, I think it really shows in this graph, fenestration products were the key and a starting point for all of that to happen. Of course, there were a lot of uncertainties about other pieces inside construction, but if you haven't seen this report, I would definitely encourage you to go to the Vancouver Economic Commission website, download the report, and then go to the fenestration page. I think their analysis is very interesting about how the high performance windows are going to overtake the market, and how this market is going to grow, which we are going to talk a bit about so that there is more context on this. But before I get us started, I want to ask you a question that hopefully also talks about the sort and kind of the areas of the buildings we are going to talk about. So spend a few seconds thinking about this. From these two photos that you see on my screen right now, so on the left we have small buildings, two, 3 stories, some single-family homes, and on the right we have big high-rises that are actually very close to each other in a dense urban core. This is Vancouver, of course. Which one of these do you think will be a bigger high-performance market for fenestration products, or generally for high-performance building products? So give it about 10 seconds maybe, and then I'll let you think about an answer, and then we can take it forward.
We've got one vote in here for single homes.
Well, that's pretty great, and I hope that everyone at least have thought about the answer that they think about. But Mike, yes, the single homes, there are different ways to answer this question, but if you want to think about the volume of construction, the single homes are going to be the leaders in the market, and our firm also primarily focuses on that market. So when you look at the landscape of construction in Canada, there are two things that are at play here. One of them is the total area built in square meters. We have around 2.5 billion square meters of buildings built across Canada of heated space, which is astonishing when I think about it. And we also have the cost of construction for building one of each of these archetypes. So a house doesn't cost a lot to build on an individual level, but it also has a lot of volume in terms of the total construction happening, and also the existing construction inside across Canada. We also have, as we go into the larger construction, so high-rise apartments, which is just 3.6% of the market in the last numbers that we have. They of course cost a lot to build, they have great margins, but the square footage of them are very small. We call these the left column, which is the single families, and the right column, which is the high-rise apartments. And we really focus on the single family homes because we think this market is really untapped. There is a lot of potential in there, and the necessity of the carbon emission reductions really comes from there. And if you look at this landscape of the single family market, of course, it extends to all of the constructions, including commercial, the takeaways we will have in this presentation. But the landscape of the single family market was dominated by the prescriptive requirements before. And I think a lot of us are really familiar with these illustrated guides. They have a page that shows what is the minimum code requirement for each part of the building. And these minimum code requirements were typically what you would meet and you would be fine with it. So the windows and doors, as you see in blue on the left, was USI 1.8, and the skylights were 2.9 for the particular illustrated guide that I picked up. But in reality, the interaction between different building components are very much more complex than what we are dealing with here. So we know that many of the manufacturers, they would primarily goal set as what they can build to these minimums, or slightly better than this, and they would set that as their product line, and they would roll that out. But the goal-setting landscape, when it comes to manufacturing products, even if there is a minimum in mind, has already changed. And the reason that change is necessary is because of the way these different components in the building interact with each other. So for example, let's take a look at a wall section and a window inside it, embedded inside it. This wall section that I put here, this white area that you see, it's transmitting about 1/4 of a watt per square meter. But the window section is of course much weaker. It transmits a lot more heat, so it transmits 8 watts per square meter. The window is rather small in the wall, but when we do a total heat loss calculation of the two systems together, with the window being embedded inside the wall, we get the total heat loss of 1 watt per square meter, which is 4 times the amount of the heat loss in the wall alone. So all of that heat is escaping from the window, and that's enough to really diminish the performance of the two systems. And it gets even much worse when you increase the size of the window. This relationship is not linear, so having something like resembling a patio door is going to get that up to 10 times the transmission of the wall system alone. And when we look at the result of the prescriptive requirements across Canada, we see that these problems with the realities of heat loss inside the buildings have caused a lot of issues. The average house in Canada, based on the 2015 data, is spending enough energy to boil up a large swimming pool. So think about it. This is not even a bad, like a poorly constructed house in Canada. This is an average house in 1 year. And the amount of heat, the immense amount of heat that we need to just put in to heat the homes not only creates a climate problem, of course, it creates a comfort problem, and it also makes people less happier to use their spaces with a lot of fenestration products, or basically a lot of heat loss. So I don't anticipate to be any questions at this point of the webinar, because we're very early on, but just a room we have between the two sections. So Mike, I was wondering if there were any questions proposed so far.
Nothing so far.
Perfect, thank you so much. So now that there are no questions, I am going to ask another question. So imagine this is something for you to think about before we really dive into one of the answers to it. Imagine you are given a building. This could be an existing construction, could be your own house, could be a friend's house, could be something that somebody is designing to build, and they have the design prepared, so they know where the windows are going, they know where the roof is going, and they now want to put their insulation and assemblies in such a way that maximizes their efficiency, the overall efficiency of the building. And as you can imagine, because of all of these interactions, it's a little bit of a challenge to really find the right combination. Where would you start, and what would you improve in their initial design to get the best bang for the buck for them, essentially, get the best performance increase without necessarily a very high increase in their construction costs? So let's think about it for about 10 seconds, and then we will dive into the answer. I wouldn't be too surprised if almost everybody here would have said better windows. I guess we are, after all, in a group of window people. But the average person may have been really thinking about the roof. They may say that I have learned that the roof is the heat goes up, so I will spare no cost, really try to improve the roofs, give a really high performance roof at spare no cost really on it, so that we really keep as much heat as possible, keep that warm air inside. And then they would go around and find a simple window and a simple boiler, and they would think that the job is done by just blocking that path of heat transfer through the roof. Now, how well do you think this building is going to perform? If your answer is poorly, I think that you won't be surprised, but a lot of people get surprised thinking about the overall performance of this building. It's going to cost a lot to build or renovate, but the overall performance of it is not going to be really good. We talked a little bit about why, but if it's still not really clear, the simple example we like to provide is, imagine you are going skiing on a very cold winter day, but you are going skiing in shorts. Of course, you are very uncomfortable losing all of those heat through the legs. You put on a jacket. Still uncomfortable, you put on another jacket. But if you go skiing in shorts, you are going to be uncomfortable no matter how many jackets you put on. And if that example translates, think about this case, that the roof is those multiple jackets and the windows are those exposed legs that are letting all of the heat to go. When we work on a building, we typically try to make it so that all of these components together are working much better with each other. We try to save at the parts that are over-insulated and spend the savings on the parts that marginally will create much more performance at a slightly higher amount of cost. So you will get better buildings that are performing much higher, but the cost of them is also quite controllable. And when you see these two examples, you will see that, well, the windows have costed more between the first case and the second case, but the overall performance has actually been better, and the cost as well. So before we dive into the performance-based system, which is the step code, and I think you all probably know what we are talking about, but just a quick primer, I was wondering if there are any questions which have come up, Mike.
Nothing specific. We did have a couple of comments, guys, that expected the roof performance or improving air circulation would have the biggest impact. So your expectations were right on the money.
Great to hear it. Glad to hear it. The air tightness is definitely something that we kind of abstracted away and simplified there, but extremely true. And it really depends on the case by case, depends on buildings. But the typical building may really have a different landscape than the guesses and the intuitions of the builders out there may give them. And that has been at least something we have seen, and we are going to talk about a case study as well. Now, the BC Energy step code, I won't really get into the details of that. I think there is so much good material out there, and it has been talked about so much that it's really not necessary to spend time on it. But essentially, every few years, the minimum of the requirements inside the BC is going to go up until we reach a net zero ready home. And when you look at the heat losses of a net zero ready home, you realize that this sort of home can be heated up with a hair dryer. So that's why we have a hair dryer here. Of course, it's quite a bit of a jump from where we are right now until that becomes just a normal. Heating up a swimming pool all the way to just using a hair dryer sounds very impossible, and that's why the challenge is much more appreciated, and there is so much force behind it. Now, we talked a little bit about the heat transfer in the building. So, another way of looking at the heat transfer is heat being water and the building envelope being the bucket. What we were previously doing was really trying to make the bucket based on a formula, but with the performance-based laws, with the BC Energy step code, we actually start to look at the leaks around the bucket, and we are trying to plug those leaks. We don't really care about the parts that the bucket is doing well. if in this photo that I have, if you make the walls of the bucket thicker, you still keep losing that water, which is a kind of a representation of the heat in the building. So instead of really looking at the individual components of the building, those are kind of blurred out in this photo, and we are really trying to look at how all of these play together to really create that nice enclosure for us and also the people that are going to live in the home. So these performance-based buildings, they are creating opportunities for improvement that we are going to leverage to really get there. And the essential part of getting the high performance buildings comes from two primary components. One of them is the building envelope, which is the kind of the walls and the roof and the windows and the skylights and the doors. So all of the things that you have around kind of the structure of the building, keeping the space warm. We also sneak airtightness into this. We kind of call it the building envelope, although I think many people might have different ideas about it. But the envelope piece, the way that these different pieces are tying together, well, essentially is the airtightness. If we have the best window installed in a building, but the cold air is just leaking around it and it's going in the building, of course, the value of the envelope piece is going to be nullified. So airtightness, we believe, is a natural part of just good construction practices, good envelope practices, and it just makes sure that these different components are connected with each other in a very strong and durable manner with good practices that make sure there is not a lot of condensation and coldness on different parts of the buildings. And somewhat tangential to our conversation today is the mechanical system, which is about heating and ventilation and hot water. Generally, these are the easier to replace components inside the building. So of course, the renovation projects generally start to think about those. But when you think about it, in reality, the mechanical system always comes after. If I'm ever asked what is a high performance mechanical system, I would say a high performance mechanical system is the one that never turns on. And if you make a building that is so great that doesn't even need a high performance boiler, or it doesn't need the best of the class heating system that is out there, well, of course, then it doesn't really matter what the mechanical system properties are. When you have a good building envelope that satisfies the needs of the building passively, then the mechanical system is going to be the need for the mechanical system and also the size of the mechanical system can be reduced. And that is the conversation of right sizing. Now we are going to get to how and why this shift in the way of thinking is actually going to redistribute the funds and the attention in a construction project that is spent on these two different parts. But if you look at the documents out, the material that is out there, the high performance building generally is considered an envelope first approach. So envelope first, alluding to what we just talked about, the building envelope takes precedence because it creates the demand for the mechanical system. And if you have a really good envelope, we don't really need to rely on the mechanical system to compensate for the deficiencies of the envelope piece. And talking about these building envelope and the mechanical systems, we have seen an 80-20 scenario in construction where the first 20% of decisions actually bring 80% of the results out of the building energy performance. This could be in the way that the shell of the building is created. It might be creating a lot of surface for the envelope so that there is more chances of heat loss. It could be the boundaries and the restrictions that the construction design team have put inside the project have taken away all of those opportunities for easy, low-hanging fruits when it comes to energy performance. Or it could be some other directions that actually helps the project. The first decisions are built and made based on science. They are done very strongly based on experience and the trained intuition of building science. And that means for the rest of the project, the construction really benefits from the strong foundation. And some more fringe ideas about improving the performance and more costlier approaches to getting to a certain step can be avoided because of that. But the question becomes, how do you make these decisions? So when we talk about a certain design of a building, and every building, as we know, are quite different, we're talking about a certain set of possibilities that a builder is dealing with. So we may have different airtightness levels that they can hire different contractors to achieve. They may have some wall systems that are either prefabricated or are pitched by some insulation provider as cost-effective, easy to construct, available options. They may have many different basement configurations for their foundation or different roof options. So they could do an interior insulated, exterior insulated. If it's an attic, there is many ways of building that out, or having different heel heights to have blown-in insulation or different types of insulations. And I think most importantly here is the windows, where you have many options when it comes to the solar heating coefficient, the U values, the glazing. All of these things can create a wide range of varieties, even if there is a favorite manufacturer that the builder is targeting. And because of the performance-based construction, we don't really have an easy way of saying which one of these options is better than the other, unless we look at all of the possible combinations of these and look at how each one of them perform. Now, the BCS step code metrics study, if you have not read it, I think it's on I believe it's on the BC Housing website. It's really easy to find with a Google search. They looked at this challenge and they realized that there are 54 million possible ways of constructing a single house based on the number of choices that they were dealing with. And you remove one window, you add some to the square footage, you change the shape of the building, you're looking at another 54 million. So this is individual building possibilities depending on the way the building's shell has been constructed. And of course, it's impossible to look at all of these designs together to really understand which one of these 54 million is the way to go. And that creates the challenge that we are dealing with right now, moving from the prescriptive requirements, which were very clear when it came to the individual pieces of building, what you need to get, to a more holistic performance-based compliance, which is the BCS step code, that most of the projects out there come up with a compliant design and not the best compliant design. And that could essentially result in more money spent or less energy achieved, energy efficiency achieved as a result of that. So here we generally want to look at where our intuition takes us. And our intuition takes us towards looking at one component and seeing what sort of pathway it puts the builder on. Imagine there is somebody who wants to finalize a design. They have 3 window options. So they could have a high performance, high cost window. They have a medium performance and medium cost window, and they have also a low performing and lower cost window. And if it was for the prescriptive requirements, you would generally look at the most you can save. So you would look at which manufacturer just gets to the level that your building code, your city, or your client have requested, and you would find the lowest cost and you would just put that order in. But right now, each of these windows are going to put you on the path of different components elsewhere in the building if you want to meet that level of step code, because each of them is going to have different ramifications. For energy loss, you may need to compensate somewhere else, or you may need to get a better mechanical system in order to meet the code. And if you look at the cost comparisons now, because of the changes that the windows have made, maybe the cost comparison shows you that the more expensive window overall had less impact on the construction costs and gave a better performance than going with a cheap window in the beginning and then trying to compensate for it elsewhere. I think if it makes sense if we go back to the leaky bucket example and really critically think about what we are doing here. We are, again, plugging those holes. We are trying to find how we can keep as much heat in, and that means we can be more forgiving to the other part of the building. But this also has a appreciable challenge when it comes to sales. I think if you are dealing with high performance windows, you naturally now would think, well, how can I be able to look at that building design holistically and sell a more premium product to my customers, and in the meantime justify that even though they are paying me more, they are going to have less hassle along the way. And that is the emerging market, I think, that the major emerging market that the high performance windows and doors in general, because they're the weakest part of the construction envelope, they are going to create. And the answer to that, unfortunately, is not really clear, but I'm going to walk you through some of the possibilities and potentials that we are looking at and we think is going to solve that problem. So looking at this, well, now we want to pretty much really narrow down on each of the construction specs, but in conjunction with each other. And if you have been following, you realize that because of all of these complexities, there is no step 3 window and there is no step 4 window. You may have gotten a call, or if you are in this industry, you may have been approached by someone who has asked you for something like that, who has asked you, can you give me a step 4 window? And of course, the answer to that is there is no such thing. It really depends on your particular design for your climate, for the necessities of the building, and you will need a very certain properties when it comes to building out the specs around the home, and those specs can really vary. So we have solar heat gain coefficient when it comes to the amount of heat that can be introduced inside the home and can offset some of that envelope loss. And then we have the U value, which is reducing the heat loss inside the from the window out to the outside. And those are the things that the step code really cares about. Now, what the right numbers for those are, that depends on the building design, but you probably do not want to be conservative with them, and you probably want to look at the rest of the design critically and look at how improving these numbers is going to improve the conditions for you elsewhere. So at this point, I am going to jump into a case study and show you a method of kind of tackling these complexities, or at least how we approach these complexities usually. But I think it's also a good point to ask whether we have any questions so far.
Well, I think you're explaining everything really well. We're not getting a lot of questions here. There is a comment here. Thank you for saying that, as we're constantly trying to explain to the industry that step code does not have prescriptive requirements to the U value and solar heat gain depending on which step the building is. So yeah, I think probably everybody here can agree with that. It's more than a little frustrating to constantly be asked by guys to provide a step 3, especially when you're going, well, step 3 in Whistler and the Okanagan and Prince George and Vancouver are not the same.
Very, very exactly. Yeah, thank you for bringing that up, Mike, and thanks for the comment, whoever that provided that. We definitely have seen that as well, and it's when I think when it establishes itself, it's going to make a lot of sense. But there is definitely an education piece that is still ongoing, and a learning curve, maybe a somewhat steep one that all of us need to deal with. So I hope that this material is useful. Either I'm doing a terrific job at explaining everything, or a terrible job. I hope it's not a latter, that we don't have any questions. But overall, I hope that these examples are helpful. Maybe a skiing example would give some of the outsider people some insight from what we have seen, and really help them appreciate the reward, and at the same time the challenge that the changes have presented. And the case study that I'm going to provide for you is also a segue there as well.
Sorry, Arman, can I just interrupt? We do have a question here that I think will make sense before you dig into the case study.
Yeah.
What role do you think solar heat gain will play in the long term? Will a low U value be the main aim, or will high solar heat gains still be required?
Yeah, that's a really great question. Thank you for asking it, Mike. The high solar heat gain coefficient is an area that is actually not quite well represented in the energy models right now. The energy model itself has some limitations when it comes to the solar heating coefficient. For example, the surroundings of the building are really not incorporated in the building energy model. So you may have a window that is facing a wall in just the vicinity of it. It doesn't really get any practical amount of sun, or really big windows around, trees around the house, and they practically don't get any sun. But in the model, you put in high solar heating coefficient, and the model is very happy with it because it thinks there's a lot of sun coming in. The other challenge with the solar heat gain coefficient is when it comes to overheating. So classically in Canada, from the start of the building energy modeling journeys that we've had for over the last many decades, we always have focused on heating as the primary issue within the housing market. And now that we are dealing with the climate change actually quite aggressively, and the climates, especially in the interior of the BC, are going to drastically change to the levels that we will see temperatures above 30 degrees Celsius for the better part of a month in those regions when we get to 2040. The overheating is starting to be a conversation that's being had more. And of course, there are many ways to merge a high solar heating coefficient with a way of not really getting into the overheating by having things like overhangs, or really trying to have the sort of trees that expand and have leaves around the warmer months to block some of that sun from coming in. But there is a slight amount, or actually maybe not quite a slight amount of unclear pictures when it comes to solar heating coefficient right now. And I would think that the attendee and also others who have dealt with this issue are being constantly asked by the energy advisors or the different clients, the customers they have, to provide very high solar heating coefficient windows. And that is because the way the models are working right now, that just gives them a free reward at a very low cost, which is the cost of the coating essentially. But I don't see that being the case for the longer run. I actually think that there are going to be measures put in to stop the overheating conversation, the overheating potential from happening. And in the meantime, we may actually more diligently look at what is happening in the surrounding of the building and limit the solar heating coefficient numbers. And that, I guess, could be welcome news, because especially when it comes to triple glaze, there are limitations when it comes to solar heating coefficient, but the U value is definitely in the direction that everyone wants it to go, which is more harmony with the rest of the building. So that is definitely the direction to go, as the question was suggesting. The U value is going to probably be more front and center as we move forward. I hope that answers the question.
I think that was a pretty comprehensive answer. And I think you also, in the midst of that, also answered another question that was, shouldn't questions about step code requirements be directed at the energy modeler?
Mm-hmm. Yeah, definitely the energy modeler is one piece of that process, but there is the methodology of integrated design process, or IDP, that has been introduced by BC Housing and other stakeholders in the construction market, Canadian and American both, that is starting to talk about how are we building buildings and what is the issues. So we right now talked about the 80-20 scenario in the construction, that 20% of the decisions really get you 80% of the way there. But the average home, the typical home, has classically been designed in a way that the owner hires an architect, the architect makes the designs, passes it along to the energy advisor, gets the stamp, gets passed along to the builder, and also the suppliers to purchase those things and put them in. But the integrated design process is now talking about how can we loop this back and have everyone on the same table at the start of the construction process. So if the energy advisor is putting a number out there, especially when it comes to, for example, solar heat gain or U value that is hard to achieve or is out of the comfort zone for many of the suppliers out there, is going to be something harder to find than the usual, then maybe those integrated design process conversations is not only going to provide value for that particular project, but also is going to have a waterfall effect on the other projects as well. I know that there have been conversations that something has been specified and it was just not quite achievable for the realities of the market, and they needed to go back and fix it, and then design would change. So there is a lot of back and forth the way things are right now. But that sort of methodology, that thought process, is definitely going to help alleviate some of those issues, especially when it comes to the work. But yes, energy advisors are very well educated on this. They are the people who will specify these things, and I think we all hope that the modeling process is and gets more comprehensive as we go forward to actually translate to good homes and high performance construction.
Fantastic, thanks.
Yes, so let's jump into the case study, and we are going to talk about StepIn. So if you have not seen StepIn before, you can go to our website, stepin.ca. This is the flagship product that my company is providing for the builder community, and also energy advisors, homeowners, product manufacturers, which really simplifies the issues that we were dealing with all of these choices and complexities. So I will show you one example of how this benefits the user, and then we can jump into the interface as well. This is one project in the city of Vancouver. If you notice the faint red line somewhere where the arrow leads to, this is the baseline construction. This is what the construction team has built in terms of they have came up with windows, walls, roofs, all of these things together. And the graph you see, each dot on this graph represents one of those 54 million designs that we just talked about, one of those alternative variations of changing something in the building and seeing what result it gives. Now, the horizontal bar or the horizontal axis is about energy-related costs of construction. So you want to spend the least amount of construction costs for a design. You want to go to the left of this horizontal axis, and then the vertical one is the energy demand, meaning how much energy does this building need in a year, And of course, you want the least amount of energy demand. You want the building to be very efficient, so you also want to go down on that axis. So you want to be the closest possible to the bottom left corner of this graph. Now, the baseline that they have created is not good for costing nor for energy efficiency. And we look at this and we look at 3 pathways that we can improve this design. One of them is just not really spending any more money in the project, but also coming up with an overall better design. Or we can go with spending, actually saving the money inside the project and getting to the same energy levels. Maybe they have already met the criteria for meeting their certain code minimum, and now they want to save some funds. Or they could go to the really high performance construction, the higher steps of the building code, and that would essentially be possible with a marginal amount of cost increase. But just knowing that, really, we have seen it in action, that really encourages people to move on to the higher steps because of just seeing the effort that it entails. Now, in this example, we actually saw that a step-in changed the heat pump, removed the heat pump, and added a glazing pane on the window, where it used to be double glazed window, and now it was triple glazed. And it was surprising, but actually also in line with the building science concept, when you think about it, is that just improving that piece saved some money from the mechanical side because, well, just didn't need them as much. And all of this is available, the tool is available to you online, stepin.ca. If you go in there, there is a launch the app button. I have already pulled up a step-in here for ourselves so that you can see how it works out. So you have a ribbon on the left. It goes from different parts of a building design. It starts with just asking where this design is, and that's relating to the climate. So then you go to the general, you talk about what sort of buildings you're dealing with. It's a 2-story building with this sort of roofs and basements. And we talk about what sort of assemblies do we want to put in these buildings. As we talked about it, there are different choices for the builder. So they may have double glazed PVC, double glazed wood frame, triple glazed fiberglass window, triple glazed wood. It's just random choices, but you could remove or bring back one of these designs the way you want it. And you also look at the solar heating coefficients of this of these windows for each. So it will go to each of these, and it will look at the rest of the building, and it will try to see which one of the windows that you have selected here amongst all of the choices we have is going to better perform when it comes to the step code. And when you go into the results of kind of the resulting page of the software, it actually takes all of those complexities away from us and puts them inside a kind of a comprehensive simulation process. So here, for example, we are looking at the results that the software has put in together, looking at different assemblies, and then cherry picking which combination has worked really well. This design that I have in front of me, for example, this one is a double stud wall with a triple glazed fiberglass window with medium solar heating coefficient and interior insulated cathedral roofs, and our 12-inch blown-in insulation, which gives us an RSI of 7. This is RSI, of course. This is over 5 times less than R value when you make the conversion. So this design happened to be the least amount of cost that you were able to meet the BC Energy Step Code 5. Then we could look at, for example, Step 4. And the design there, the best performing design there was actually a split insulated wall with a double glazed PVC and high solar heating coefficient window and an interior insulated cathedral roof. So you see how we are kind of simplifying all of those combinations of designs together in a way that we actually simplify the choice for the builders. Now, if you go over all of these designs that we have provided, for example, click on something else, you may see that the window shape is going to be different. Let's try this one. And this one is a triple glazed fiberglass window with a high solar heat gain coefficient, which also was able to reach a step 4. So the number of choices for the builders that they are presented with is actually quite diverse, but it also captures the other parts of the buildings, and it shows how we are trying to mitigate the path of heat loss and then save in the rest of the project. Now, of course, this is like a very quick overview. I don't think I spent even 3 minutes on this, but we have a lot of educational videos there that actually show you how the software works and how you can input the design in there. We are also there to help you. We have a chat function here that you can use and ask your questions when you have a client or you want to explore this for yourself. But just to give you an idea, for example, in this particular design that I selected, and it was doing really well for the step code to help this particular home reach this design, you see that the windows were actually quite a bit of cost in the whole construction process. Construction cost, it's almost as much as walls now in this example building, which is actually not quite small. Now, if I click on this cost option, it's going to give me the heat loss for each of the building components, and we see that the windows are still getting the highest amount of heat loss. So really addressing those heat loss paths have been quite costly for the user, but it also has been rewarding. And this report, it has a lot of these features that helps you understand where you should be spending even more money if you want to get to step 5 or get safer into a step 5, what each of these construction pieces are doing. And I think it's all for the exploration, but this is our answer, essentially. This is the best answer we could have come up with to simplify those complexities of the performance-based requirements, and we hope you find it useful, or you want to come up with your own system that really captures all of the potentials for your market. So at this point, I want to make sure we have enough time for more questions. And Mike, I'm wondering if we have anything there.
No, we're good.
That is perfect to hear. So just to reiterate, so if you go to the StepVin website, you can just launch the app. It doesn't need any installation, and essentially you can input a design or look at one of our examples and build from that example onwards, and basically just get to the result and see how different window options, different roof options are playing with each other. And I can play with it a little bit more if the time permits.
There is a question. A couple questions have popped up here now, awesome. Which are fantastic questions. One, how are you inputting the costing for each of the options? Mm-hmm. And then we've also got, within the software, can you adjust the window to wall ratios as well as glazing orientation?
Absolutely. So the first question, we have been working on the costing pieces of our software for about 2 years now. Of course, the costing is a very complicated conversation. I'm not going to pretend that we have got it all right, but you can look at our cost breakdown to see how much we are calculating for the windows. And these are coming from an averaging that we have from different manufacturer outreaches, and also the quotes we have had from our own projects to come up with kind of an average to high basis for our cost calculations. And also, different parts of the software give you the option to override the costing pieces. So whenever you hover over one of the assemblies that we have put in the software, we give you an idea about the costing basis for this design, so for materials and also for the labors per square foot. And if you don't like that, you can add your own assembly. You can put in your R values and material and labor in a way that you think aligns better with your ideas. Now, as for the window to wall ratio, yes, what you are giving a StepVin and the results you are getting are for a full building energy model. Don't get this wrong. This has absolutely everything inside it, every individual window and a skylight. You put in the dimensions and the types in them. Of course, there are many ways that you can simplify this and only give one number. But in general, you put in the very simple information that should take only about 15 minutes to put in about the areas, perimeters, heights of different walls and windows and doors, the orientations of these windows and doors, as you see here. And if I want to add another one, I just add another window and I put the information in the way I want them. And then once you go to the results page, you basically get the results for this particular design, and you can export this design into PDF or into actually a HOT 2000 file, which is, I think it's a very common thing for the BC Energy step code. And also you could make comparative analysis between these designs in order to actually get the best kind of performance for your design. But yes, on a per project basis, things tend to be widely different, and the report you are getting is for the particular home that you are working on.
Well, color me impressed. I like this.
Happy to hear that. So that is, I think, the piece of the tool that we are putting out there. We hope you really enjoy it. It's available and through the website that is you can see on the screen. If you go in there, there is a launch app button that you just click on it, and you go to our kind of app interface, but it's all online. And make sure to actually hit the chat button if you have any issues, and we'll be more than happy to do it to help you with that. And I hope this presentation overall was interesting. We do publish different things on our website. We will have more of these case studies coming up, and if you are interested, I hope that you will follow us in the future.
Well, I think we should have a final call here to see if anybody has any further questions or comments. We do have a couple of guys saying it's really useful. Thanks a bunch.
Thank you, and I want to use this this period that we have, while if there are any more questions coming in, to really thank Zaina and you, Mike, for organizing this webinar. The great work that the Fenestration BC has done to bring in some of the voices and the interest together, and I am hoping that tools like the work that we are doing is helpful to steer the decision-making processes in the right direction and really get there as soon and as easy as we can to solve the challenges that our province and also the rest of the world is facing.
Yeah, for sure. We do have one question here looking to clarify where the costing data comes from. Because obviously it's such an important parameter to the accuracy of this. So then is it just, for the really accurate data, or is that going to be the input from the user, or what?
Yeah, so the costing data comes from a database of default costing numbers that Stepin has in the backend. You, of course, can override that costing database and bring in your own numbers, but we want it to always be turnkey and do not really ask users for all of their numbers. These costing data has come from engagements through 5 avenues that we have, with one of them being just surveying the available products in the market, all the way to going to manufacturers and asking for some numbers, and also like even going to suppliers and really looking at the price sheets that they have. Now, when we get these numbers, for example, prices for double glazed PVC windows in the city of Vancouver, we average all of these, take out the outliers, and also add a little bit towards it so that we don't really give users a sticker shock. and we put that number inside our database. These numbers also change depending on your location and also some other considerations for some of the assemblies. So it's actually a very comprehensive system on its own. Now, understanding that some people may want to override this because of their special conditions, we are also hoping that if you see anything that's not quite accurate with the data, you let us know. The data that the users input, we don't really rely on, or we don't ever visit. This is, if you put in your own costing data, this is for you. We're not really interested in looking into those. Overall, we are really hoping that we get the comparative prices right. Sometimes a project has some special, for example, like is remote, so there are charges to get the material there, but it really doesn't affect the bottom line, because different products have still the same differential advantage compared to other products, even though that sort of additional cost comes to all of the assemblies. In the meantime, all of these prices are energy related costs. So when you are talking about finishes or tiling, or those sort of things are not included in this pricing. And if you hover over any of the assemblies that we have, we talk about what are the assumptions for the costing, what is the numbers, and hopefully that will give you enough transparency to really understand what the numbers are coming from. But our approach is to make these costs as accurate as possible, and moving forward, we are also trying really hard to get that there. So your feedback is really welcome.
Well, that's fantastic. That sounds really good. I'm excited to dig into this myself, actually, and see how things look, see what maybe I could have done even better on my house that I just finished. I'm sure that'll frustrate me. Thank you so much for this presentation and your time. And I'm sure if anybody else has any further questions or anything like that, Arman's information is up on the screen there, so please drop him a line. And I know I'm looking forward to the remainder of these sessions that we have. They're ongoing, so sign up for them, and we'll all learn a little bit more as we move forward here. Thank you very much.
Thank you.